Hello everyone. Kotungwane, the native god here. Firstly, let me just apologize for the background noise. I unfortunately do not have the resources for cancelling out the background noise, right? So my apologies for that. But I promise you, the information you're going to get from this video is definitely going to be louder than the background noise, right? So without further ado, let's get into it. So on this video, I want us to go through this exercise based on flow through an orifice, right, for mechanotechnics and for hydraulic systems, right? Now under hydraulic systems, you get different units, and this one is based on measurement of flow. So under measurement of flow, we have flow through an orifice, and then we have Venturi meters. Right, the video on Venturi meters I'm going to upload after this one. Right, so stay tuned for that. Now let's look at the problem statements. It reads as follows: a 10 millimeter diameter sharp edged orifice is provided in a vertical side of a water tank. The center line of the orifice is 750 millimeters below the water level. The set of water issuing in a horizontal direction reaches a horizontal distance of 550 millimeters and falls 128 millimeters vertically. The set diameter of the Vanna contractor is 9 millimeters. Assume that the head of water in the tank remains constant. Calculate the following: coefficient of discharge. So they want us to calculate CD, right? Now, if you've been following my videos, you know the first thing I always look at as far as any problem is the data we've been given. Right, now for for flow through an orifice, right, we have information. In fact, for measurement of flow, you get information that is ideal, right? So ideal information is the one we take as theoretical, and then you get the actual information, right? So by that I mean, in terms of the quantities that we're going to use here, in terms of velocity, we are going to have theoretical velocity, we have actual velocity, we have actual discharge, we have theoretical discharge, right? And then in terms of the area as well, or diameter, we have theoretical diameter, and we have actual diameter. Now in terms of the actual diameter and theoretical diameter, the actual diameter is the diameter of the Vanna contractor, right? So that's the smallest part of the water jets that is coming out of the orifice, and then the diameter of the theoretical diameter is one of the actual orifice, right? Now all of this information I did share in the video previous to this one in the playlist, right? So if you haven't watched that video, make sure you check it out, right? I have a whole playlist on hydraulic systems for mechanotechnics and for, right? So I would suggest that you go to that playlist and watch that video, right? Now, let us interpret the given information, right? Now they say here, right, in terms of the information we've been given, so we have a 10 millimeter diameter sharp edged orifice. So this is the diameter of the orifice, and like I said, the diameter of the orifice we take as our theoretical diameter. So dt is equal to 0.01. Alright, now all of our quantities here we have to use as the standard, or in their standard units of measurement, and the standard unit of measurement for diameter is meters. Hence you have to convert this into meters, right? And then orifice is provided in the vertical side of a water tank. The center line of the orifice is 750 millimeters below the water level. So this refers to the constant pressure head, right, which is equal to 750 millimeters. That is 0.750 meters, right? Now, if you took notes, I did say this is the constant pressure head, right, that we get on flow of an orifice, flow through an orifice, right? Even if you look at this statement here, they said assume that the head of water in the tank remains constant, right? Now, the reason why we always assume that pressure head is constant, right, before we look at the schematic of a problem based on a flow through an orifice, I want us to consider the circuit, right? Not really consider the circuit, but I just want to explain how essentially how how hydraulic systems are classified. So hydraulic systems are classified into two, right? You have an open loop hydraulic system and you have a closed loop hydraulic system, right? So the circuits that we have in front of us is for a hydraulic system that is classified as an open loop hydraulic system, right? So there is one way. So this here, right, this is a schematic illustration of a tank or reservoir, right? So all of these, right, I know it seems like there's three of them, but essentially it's just one, right? It looks better if you draw each section, you give each section its own sort of like tank or reservoir symbol, right? But essentially this is all just one tank, right? Now what typically happens in an open loop hydraulic system is, so water or the fluid is drawn from the reservoir, right? It does the work, and then on its way back to being drained, right, it is drained back into the reservoir, right? So because the fluid gets drained back into the reservoir, that is why we consider that as an open loop system, because the fluid is drained back into the reservoir, right? Hence, this here, which I'll explain just now from the perspective of the schematic illustration of a flow through an orifice, right? The reason why the pressure head remains constant is because the water level or the fluid level on the reservoir, right, it remains constant because the fluid being used is always drained back to the reservoir, right? And then of course you get a closed system, right, a closed loop system where the fluid is initially drawn from the reservoir, but instead of going back to the reservoir, right, it essentially goes back to the pump, right? So that one would go in this direction as opposed to going back to the reservoir, right? So that is to say that hydraulic systems based on flow through an orifice are essentially open loop hydraulic systems, right? That is why the H is able to remain constant. Excuse me. Right, now this here is a schematic illustration of flow through an orifice, right? The H that we are referring to, or the pressure head that we're referring to, is this one. When we say that the pressure head remains constant, or the head of water in the tank remains constant, it is this head, right? So we take point 1 as this one and point 2 as that one, right? So if you look at both point 1, so point 1 is essentially at the vena contractor, right, of the water jet, and then point 2 is at the vena contractor, right, of the water jet, and then point 1 is on the inside of the reservoir, right? But what you should take note of here is that point 1 and 2, right, point 1 and 2 are coaxial, right? So they are on the same set of axes. So that will be point 2, and point 1 will be, say, somewhere here, and that will be point 1. Now if you look at both points, right, they are coaxial, right? That is why we say that because this hydraulic system is an open loop, hence the fluid or the water essentially returns back to the reservoir, right? That is how this pressure head is able to remain constant, right? So the pressure head difference will be the H of water, right, from the water level to essentially 0.1, right? This is the H we're referring to. That remains constant, right? Again, go back to the video where I explain the concepts of measurement of flow, right? Right. So our H remains constant. That H remains constant. And then the set of water issuing in a horizontal direction reaches a horizontal distance of 550. So that is to say that the X distance of the water jet is 0.55 meters, right? And then it falls 125 millimeters vertically. So that's the Y distance of the water jet. So there will be 0.128 meters, right? The set diameter of the vena contractor is 9 millimeters, right? Like we said, you get the theoretical diameter and you get the actual diameter, and the actual diameter we take as the diameter of the vena contractor, right? So this would be dA, actual diameter, which is equal to 0.009, right? So that's the information we've been given, and we've been asked to calculate essentially the efficiency of the pump, which is the same as the coefficient of delivery. Right, they want us to calculate CD. Right, so in every problem that you might be looking at, you have to, in breaking down or in unpacking what it is that you have and how you are going to get to, or what it is that they're looking for, right? You have to consider how you are going to get to what they are looking for, right? And remember how this is calculated, right? So CD, right? CD is calculated either using the discharge, right? So you have an actual discharge and a theoretical discharge, right? Or you can get CD by using the hydraulic coefficients. That will be CV times CC, right? Now we know in order to get this, if you're going to use this one, we need to get QA and QT. If you're going to use this, then we have to calculate CV and CC. Right, so that's the first thing you establish. So we know now that you're either going to need this and this, or this and this. Now the question is, how do you get to either this or this or this or this, right? Either way, in having to calculate both of these quantities or all of these quantities, right, you are going to need, remember that Q, general formula for calculating Q is the area times the velocity, right? So meaning to get Q, you need the area, which we have the diameter, so we can get the area, and then you also need velocity. So you're going to need the theoretical as well as the actual velocity. Similarly, with having to calculate these quantities, right? To get CV, you need the velocity. To get CC, you need the area. So either way, right, you need these quantities, right? So after having established how you are going to get to what we are looking for, you then start doing your solution. We know we have to get the velocity, so we calculate our velocity, right? Based on what we are given, we are able to get both the actual and theoretical velocities, right? Remember that actual velocity, right, is equal to x times the square root of g divided by the square root of 2y, right? So now you substitute, right? X from our given information is 0.55, right? To multiply that by the square root of g is equal to 9.81 for mechanotechnics, right, divided by the square root of 2 times y. Y is 0,128. Right, now if you punch this in your calculators, right, you should get 3,405. This is in meters per second. Right, now you calculate your theoretical velocity. Right, your theoretical velocity is equal to the square root of 2g constant pressure head, right, or constant water head. Right, and then now you substitute. So this is the square root of 2 times g is 9,81, times the constant h, which is 0,750, right, and then if you punch this in your calculators, you should get 3,836 meters per second. Right, now this is all about having understood, right, one, how hydraulic systems work, and also specifically how the concept around flow through an orifice, right, in terms of the involved quantities, right, that is the wide distance of the water jet, right. I'm speaking from the perspective of because I know students sometimes confuse the wide distance of the jet, or the vertical distance of the jet, right, with the constant pressure head, right. There's a major difference between the two, which I explained in the beginning of this lesson, right. This here refers to, right, if we just quickly go back to the schematic illustration of flow through an orifice, right, this here is our water jet. So y represents the wide distance, or the vertical distance that the water falls, right, and then of course x is the x distance that the water falls, right, whereas h, right, is the distance from our reference point to the water level, right. So make sure you don't confuse the two, right, make sure you don't confuse the two, right. So now we have VA, we have the actual velocity and the theoretical velocity, right. So now we can calculate, say we calculate CV, right, calculate the hydraulic coefficients, right, because at this point I know if you've been doing hydraulic systems, right, you have already been dealing, or you already have been using the continuity equation, for instance, right, where we know Q is equal to AV, right. So that is why I'm taking the approach of having to calculate the hydraulic coefficients, right. Aside from that, you of course can take this approach, right, in having to calculate CD by first calculating the Q's, so your theoretical and actual discharge, right. You can take this approach because at this point we have both the velocities, theoretical and actual, and essentially we have the actual and theoretical areas, seeing that we've been given the diameters, right. But like I said, I'm taking the approach of having to calculate the hydraulic coefficients, right, so we get used, or we familiarize ourselves with that approach as well, right. So I'm going to calculate CV first, right. CV, that's the coefficient of velocity, that is equal to VA divided by VT, right. And what is this equal to? VA is 3,405 divided by VT, which we got 3,836, right. And this, if you punch this in your calculators, you should get 0,888, right. Now this here is a coefficient of discharge, and all hydraulic coefficients, right, are dimensionless, right? As you can see here, it's velocity over velocity, so the SI units of both essentially cancel each other out, hence we are left with no dimensions, right? Then we calculate CC, which is the coefficient of contraction, right? That one is essentially equal to the actual area divided by the theoretical area, right? Now remember that area, right, when we speak of area for what is this, the actual area and theoretical area both are circular, hence in calculating area we use the area of a circle, right? So this would be pi over 4 times dA squared divided by pi over 4 times dt squared. Now of course mathematically this and this cancels, hence to calculate the coefficient of what is this, contraction, you can simply use dA squared divided by dt squared, right? So you don't need to do all this, right? You can simply say dA squared divided by dt squared, and I just explained why that is, right? So dA, right, dA is 0,009, so this will be 0,009 squared divided by, right, 10 millimeters, so 0,01, so 0,01 squared, right? And our coefficient of contraction is equal to 0,81, right? Now based on the approach that we took, right, based on this approach, we know that we are now going to be able to get the coefficient of discharge, right? Remember in the beginning we said we can take either of the two approaches that we can take here, that is either by using Q, right, so QA divided by QT. So if you calculated your Q's, right, this is the one you would use, right? It would suffice, right? But remember that this here is equal to, now Q is VA times the actual area, right? So this is the equivalent of QA, and then the equivalent of QT is VT times AT. Now if you further break this down, right, we do know that if, for instance, mathematically, right, we say we take this as one term and we multiply it by taking this as one term as well, meaningly we could say that this is equal to VA divided by VT times AA divided by AT, right? And that is where essentially CV times CC comes from, right? Now this was just for interest sake, because we have calculated our CCs, it means this is the approach we are going to take, right? And then of course if you calculated Q's, this is the approach you are going to take, right? So here we calculated our coefficient of discharge, what is this, our hydraulic coefficients. So we are going to use CV times CC, right? And CV is equal to 0,888, CC is 0,81. And then if you punch this in your calculator, excuse me, this is going to be 0,71719, right? So if you used the other approach, you should get approximately the same thing, right? Could be 0,72 something, right? Either way, approximately it will be the same, right? And that is how we approach such questions, right? What is important here is understanding the concept, right, of this kind of hydraulic system, right, how it works. And the of course, quantities that are involved, right? How we look at the hydraulic system from an ideal perspective. So by that we mean when we are not considering losses, right? And how we look at it when we are considering losses. So for instance, remember we get major losses and we get minor losses. Now at this level, so Mechanotechnics N4, we only consider major losses, and major losses are your frictional, right? Your frictional losses, which we refer to here, or we normally use it as a frictional head loss. So those are your major losses, right? So if we do not consider this, it means you are looking at the hydraulic system from an ideal perspective. And when we do consider losses, right, it means, or when we don't look at the hydraulic system from an ideal perspective, it means we are, or we have to consider this as well, right? All of this, though, I did explain in the video where I explained the concepts of flow through an orifice. So if you haven't watched that video, go to my playlist and definitely check it out. Right, I hope you found this helpful. Right, next I'm going to cover Venturi meters. Right, yeah man, see you on the next one.